I went to a small country school, Harden Area School, and I've always loved colour, and introducing me to permanganate at school really set me off in chemistry. It's a beautiful colour, and as you add more and more water, it just retains its intensity, as you can see there. Hi, I'm Sally Brooker, and I'm at the University of Otago now and continuing on in chemistry. An aspect that I particularly like is not only the colours that you can get, but also that you can grow crystals of these molecules, and that means that we can work out what the three-dimensional arrangement of the atoms are in these molecules. So my research group is focused on making new molecules that hopefully have interesting properties, and the structure or the arrangement of atoms in 3 dimensions is very important to the properties that we see.
These beautiful blue crystals that you can see here are copper sulfate crystals. Hi there, I'm Jason Price. I'm working at the University of Otago. I've been growing crystals for quite some time here now, and the important part of growing crystals is it gives us a window into seeing the arrangement of atoms within those crystals itself. The process of growing crystals is quite simple, with taking, for example, the copper sulfate, dissolving it into water, and then taking that solution and allowing it to slowly evaporate. This then allows us to grow quite large crystals, as you can see here. Copper sulfate, however, is a very simple array of atoms, and it's very easy to grow large crystals of it. A lot of the materials we work with, they're very difficult to actually grow crystals of. So if we can get a crystal that's of 1/10 of a millimetre in dimensions, then we're thrilled. It's excellent. It's just such a good thing.
Before we grow our crystals, we have to make our molecules. To do this, we have to weigh out the materials that we use very accurately on the scales. Hi, my name's Andy Noble, and I work at the University of Otago. So here, I'm going to demonstrate one of the reactions that we do to synthesize the molecules that we make. I'm going to dissolve this material here, which is iron tetrafluoroborate, in methanol, and also our ligand, PMAT, in methanol. So we turn on the magnetic stirrer, and the material should dissolve. As we add in the iron, the solution should change colour. This is an indication that the molecule we're looking for is forming. So hopefully from this, we will be able to isolate crystals that we can analyse. So the molecule we have here that we're interested in, we need now to form crystals of. To do this, we use a variety of techniques. One such that I'm going to demonstrate now is called ether diffusion. So the molecule we're interested in is dissolved in methanol here, so it's soluble. So what we want to do is to create an insoluble environment where the material will slowly crystallize out. We can do this by adding it to an ether jar. This is a technique called vapor diffusion. The ether vapor should diffuse into these vials, and very, very slowly what we should get is some very, very small crystals. So after a few days of vapor diffusion, the material that we're interested in has become insoluble in the vial. So if we look in the vial here, although it looks like there's a very, very fine powder, there are actually thousands upon thousands of tiny, tiny crystals in here, and these crystals should be suitable for X-ray analysis. So hopefully we'll be able to determine the structure of the material in the vial, and we think that it may look a little something like this.
The crystals that we've just seen may have looked like a powder. However, when we look at them under the microscope, we can see that they're perfect for X-ray diffraction. Hi, I'm John Kitchen, and this is where we start the process for determining the structure of the atoms within our crystals, where we pick a suitable crystal and mount it on a loop. So now that we've selected a crystal, we can now move through to the X-ray diffractometer and mount it. The first step in this is to put the crystal in a cold stream here, which is set at around about minus 184 degrees. And this locks our crystal in place, and you can now see that the crystal that was yellow at room temperature has now changed to a purple colour. The diffractometer works by firing X-rays through this tube here, through our crystal. These are then diffracted and detected on this area detector here. And in order to ensure that the crystal is always bathed in X-ray beams, we have to physically centre it so that no matter where we move the crystal in space, it stays centred. Running the crystal overnight, we get a diffraction pattern as seen on the screen here, and we can use these spots to determine the structure of the crystal.
Here we have the molecule as revealed by our X-ray crystallography experiment. You can see now we can identify all the atoms in space, and we know it's three-dimensional structure. In the centre we have two ion centres shown in green, and bound to those we have these nitrogens which are shown in blue. You see there are 6 around each ion centre, and the carbon atoms are shown in black. So this overall we have 2 ion centres sandwiched between 2 ligands. Okay, you may remember that we took our colourless crystals and put them into the X-ray diffractometer's low temperature stream. They went from colourless to purple. Now we got quite excited about that because molecules don't often change colour when you change the temperature like that. So we decided it would be a really good idea if we could determine the structure of the colourless form as well. So we did another data collection on a room temperature setting. Here's the structure shown here. So once again our ion centres are sandwiched between the 2 ligands. But interestingly, when you're at this colourless form, both of the ions are identical to one another. They have exactly the same electronic configurations. In contrast, if we go to our low temperature data collection, which remember the crystal's purple at that point, we see these 2 ion centres are now different from one another. And in fact they differ in their electronic configurations. Now that might sound like a pretty small difference, but obviously it had a big impact on the colours. We went from colourless to purple. Now we're quite excited about this sort of colour change as a function of temperature because it effectively is an on-off type switch. It's purple or colourless depending on the temperature. So it's a binary code, 0 or 1. And so ultimately it may be that molecules like this can become molecular sized switches for use in molecular computers.